Hello and welcome to this third video about PWM and Dual PWM, and specifically how it relates to modular synth DIY audio and control voltage signals. So in the previous videos we've learned how it works, and then we've learned how to set it up in the Arduino so it won't get too much interference from the PWM being too slow in the audio range. And we finally talked about the resistors that had to be an exact match between, if we have 16 bits, so you had to have an exact match between one resistor value and 256 times that resistor value. So you've had a few weeks now to meticulously find these and measure these resistors. You found the correct values, and now we still need to smooth out the signal, because it's still a PWM signal, and if we use it for CV, that will really not sound good. It will probably sound quite good as an audio signal, but it will sound even better if we smooth this PWM signal out so we get a steady voltage or a nice analog waveform. And the way we're going to do that is with a filter. So we're going to go through a few filters that has been made and how simple it can be, and maybe we can find a bit more advanced variant to see if that makes it even better. But before we do that, I want to say thank you to my Patreons who support me over on Patreon, of course, and yeah, make some of these things possible that I do here. So thank you very much for that, and hope you get a few interesting things more over there. So with that said, should also say that if you're not on my Discord and you like this kind of stuff, you should really go there, because there is a lot of really nice people there. We have really nice conversation. People help each other out. There are lots and lots and lots of really cool projects going on over there that I have nothing to do with, that all these other people are doing over there. So can really recommend that if you're not already there. Let's start by explaining what an RC low-pass filter is. RC stands for resistor capacitor, and this is an RC filter. It is a resistor in line with the signal and a capacitor down to ground. If we were to switch places on these, just to get that out of the way, this is an RC high-pass filter. This is not what we're going to use at all. That would really take away the function we want. We want an RC low-pass filter. Resistor in line with the signal and a capacitor to ground. This is a simulated PWM signal that oscillates between 0 and 5 volts at a rate of 20 Hertz and at the carrier frequency 31.3 kilohertz. So basically what we have in the previous videos about the output from the Dual PWM. And if we run this, first we see the capacitor go up to about, it is almost up at the top here, so it takes 2 milliseconds. It's taken 2 milliseconds to get up here, and that is charging the capacitor. And now we see this happens. So actually, let's start by showing you this. So this is the signal coming out. This is the PWM signal, and it's 5 volts and 0 volts and oscillates in between those. We've gone through this 100 times soon. And when we put this on, we get this little signal here. So what happens now is that when this output goes to ground, this one capacitor releases the energy it has out on the output, thus smoothing out this surface. And once we get back to 5 volts, it charges the capacitor again. So you get this little triangle square instead of the really huge square wave. And this is what we need. We need to smooth out the signal. So instead of this very jagged between 5 volts and 0 volt signal, we now have something that oscillates between 4.062 and 4.33. So it's still 0.3 volts, which is not good enough for CV, but we are getting there. And basically this is what the RC filter does. It just smooths out the signal with this capacitor, then filling in the gaps of this signal. So how do we know which values to put here? Well, you can just play along and try different things out until you think it sounds good. If we go to 1 microfarad, you'll see this. We get a much smoother signal. But this also means that it will get much slower. It works now in 20 hertz. But if we go up to 2000 hertz, let's say, we want to do some audio, this happens. So this should actually, this is a sine wave, or this is a triangle wave that should go between 0 and 5 volts. And we see it is slowly still ramping up. And it's going to stop around here, where it just oscillates around 2.5 volts. And so 2.4 and 2.403, 2.436. Because it can't, this has so much energy stored in it, so it can't really move from the voltage in this at this clock frequency. And if we go in the other direction and go low instead, you will see that the spikes will get much more prominent, because now we can't keep the time in between the pulses. This doesn't have enough energy to fill them. So for this simulation, 10K and 100 nanofarad is quite good. But if you don't want to wing it, there are online calculators. You just search for LowPass PWM filter calculator and you will find a whole bunch. I like this one by Luis Lamas, and he also explains the basic concept of an RC filter. And then we have the signal values and the filter values, where we can add them in here. And so we have 5 volts, and we have the PWM frequency 31372, and we put the duty cycle at 50%, and then we can try different values to see what we want. So if we take our the most significant bit of our dual PWM output, 3.9K, and we take a 100 nanofarad capacitor, we get a few things here. First, we get the RC time constant, or the tau, and that is at 0.39 seconds. What's tau, you ask? Well, tau, or RC time constant, is the time required to charge the capacitor from 0 to approximately 63.2%. And I don't know why this value is important, 63.2. Also to discharge the capacitor to 36.8. So yeah, I don't really know why. But down here, response time to 90% is 0.89. So basically a bit more than double that. And I think this one, the response time, is more important because this is, so 90% is at least close enough to 100%, I guess 100%. It's capacitors we're talking about, so 100% is infinity because capacitors are never fully happy. So that's why they have 90%. And that's 0.08 seconds or 0.1 seconds if we round up. And for a, let's say we want to do an ADSR, which is my next project, that could, I think, is definitely fast enough. If it's not, I guess we can go down a bit. So here we can see 200, then it goes up. So if we go down to 50 nanofarads, 0.5, then 0.05 seconds, which is good. And here we also get the ripple. And here we see that the ripple is bigger when we have a smaller value and smaller when we have a bigger value, just like what I showed here when we moved up and down with the values. So here you can find the correct resistors and capacitors. Now here comes the thing that got me sidewinded in this project, and that is, so this was for one of the resistors, but we have two resistors, and if we look at the Open Music Lab website, we see that they both resistors just go out to the output and one capacitor to ground. So I started thinking that, well, then you have a 1000 or a 1 mega ohm resistor. So then I thought, you have 1 mega ohm resistor, and well, you have the same capacitance because it's just one capacitor. Then the tau will be 10 seconds or 23 seconds before we're up to 90%. And let me tell you, that is, well, it's not the fastest ADSR in the world. I was thinking too long about this one without asking anyone. But then I finally manned up and actually asked the question on the Discord server. And asking questions is very underrated, especially in the DIY community. Is always so helpful. On the Discord, there are so many knowable people there and so many kind people that help each other and so many cool projects that people are doing. So really check that out if you haven't already. So anyway, I asked the question there and gave this example and also showed them a simulation in Falstad. And well, first answer, can't you just ignore the big resistor since it's parallel to the small resistor? Much bigger. Landertronic does this all the time with his analysis. Didn't really understand this. And then I actually had to, life happened and I had to run away from the keyboard and the discussion started. Lots and lots and lots of interesting information and stuff. But the thing that happened is Luther and Locrius started a big discussion, which ended in this wording here. To word it differently, the settling time is a function of time and amplitude. The 1 mega ohm path is much slower. The RC cutoff is 256 times as low. But the amplitude is also much lower, namely 256 times, the mixing ratio. So that balances each other out. So in this here, we're not really talking about 5 volts. The whole thing is swinging between 5 volts, but the 1 mega ohm resistor, the values there are just 1/256th of that value. So it doesn't. So even though the settling time is much slower, because the voltage is much lower as well. They cancel it. It's lost in the, because it's so small. It's 256 times smaller, the value of the voltage coming out. So it is lost in the bigger value. So we can neglect this, the 1 mega ohm resistor, and then just work with the 3.k ohm, which then gives us this with a ripple of 1392, 1474. So quite a bit of ripple still here. So what do we do then? We found this middle value here, that it's fast enough, but a little bit too much ripple. Well, what you can do is you buffer the signal and you put another low pass filter after it. So that is what we've done here. Here we have the Dual PWM now, and they are a bit different. This one is at 40 Hertz, this one is at 35, just to have a ever-changing curve all the time here. And now we see it is much better. If we look here, we go from 400 millivolts to 9 volts, and this takes what, 1 second there, and so that is 15 milliseconds. That's the, we can go faster, but we see here, and we see how smooth this curve is. There is just 0.001 volt slowly moving up here. So we have the first filter here, and then we buffer the signal, or actually we amplify it. So we take the signal times 2, so we get up a bit in voltage here, and then we smooth it out again with a 1K resistor and 330 nanofarads. And again, this is then it's not really a second order low pass filter, but it is 2 low pass filter after each other, and the calculation doesn't work anymore. If we go in here and write 1K and 330 nanofarads, we get a ripple of 2.3 volts and 0.00076 seconds in response time, which is good, of course, but it doesn't really add up to what we see here. So in this case, I've just picked a value that I thought makes the curve look good enough. So if we take this to 100 instead, we immediately see that this curve starts to wobble a bit. Not that it's still thousandths of a volt in difference, but yeah, it just looked good. Probably this one would be enough as well, and I would say I'd have to just elaborate until you find a good signal with this setting. So I took the simulation of the simple low pass filter, just one, not the op amp, put it on a breadboard and put it into this really sensitive VCO, exponential CV input. And what you hear is it ramping from 0 to 16,000, and every time the LED turns on or off, it starts a new cycle. And except for the fact that it is actually slow in the beginning and fast in the end, it sounds like it is very even. there's no jumpy bits. I did try it with the amplified output that I showed also in the simulation in the Felstad. Did not work as well. Might have fried the op amp, so I'm gonna build that again and see if we get that working. So here's the second circuit with the second order low pass filter and the amplification by 2. Happens to be that you need to create the correct circuit for everything to work and the op amp not to burn up and stuff like that. So here's the correct circuit with a 330 nanofarad capacitor, and well, as we can hear now, we have a bit longer range, and that's because now it should be around 0 to 10 volts instead of 0 to 5 volts. So that should do a bit of difference there. And also let's check the PWM. Need to turn that down a bit because the range is a bit too... I don't hear the stepping at all like I did in the last one, so that could have fixed this one as well. So this looks promising for future projects at least. What can we say about this? This took way too long for a simple project like this was. That's what happens. Sometimes you just get caught up in, or at least it happens to me, I get caught up in a question or in something, and if you get caught too long, I actually just lose motivation. It's a problem I have, I guess. But we finally fought through this, or I fought through this, and I think I got a good concept now to move on. And as I mentioned earlier in the video, I want to do an ADSR with this programming skills, this kind of circuit. So hopefully that will work. I am how I am, so I've already made a panel for the ADSR, and I have a bunch of ideas that we're gonna go through that in the next episode, of course, where we hopefully can do some coding, and hopefully this will work as I thought it's intended to do. But we'll get back to more on that in the next episode, I guess. Thanks for watching, and sorry for taking so long, and yeah, hope you learned something. I know I did. Never take anything for granted that it should be easy. It's never easy, seems to be. Even the simplest concepts, once you start digging, it's a lot of interesting caveats that you need to figure out. Anyway, have a great time, and I will see you in the next video. Take care. Bye.